control for the given chemical process. That is the question number 4. And the last question is how the information taken from the measurement used to adjust the values of manufacturing variance. And all these 5 questions we have seen little bit in detail in the last class, isn't it? Correct? The first 4 questions are very much straightforward, isn't it? Answer for the first question is we use process control primarily for 3 reasons, isn't it? Suppressing the effect of disturbances, stabilizing the inherently unstable process, and optimizing the process. These are the 3 reasons for which the process control is called upon. Then what are the variables which we have to monitor continuously in order to see the performance of the process? So usually in a certain heater system we have to monitor the height, we have to monitor the temperature, isn't it? In case of a distillation column we have to monitor the quality of the distillate and quality of the water product coming out. In case of CSTR we have to monitor temperature, concentration and flow rate, isn't it? So depending on which system you are looking at, which variables you have to measure continuously in order to monitor the operational performance of the process, that you can figure out. Third question, which variables you have to manipulate, isn't it? So in a certain heater case you can manipulate the inlet flow rate, outlet flow rate, you can manipulate the steam flow rate to the tank in order to maintain the temperature, isn't it? Similarly, in case of certain reactor you can manipulate the coolant flow rate to the reactor, isn't it? In case of distillation column, you have to manipulate the reflux ratio, isn't it? So depending on which system you are looking at, you can figure out which is the appropriate manipulating variable which you can change at your own discretion in order to add the external intervention in the system. Okay. Again, this is the last. 4th question is which control configuration is the best, isn't it? So you have multiple choices with you, isn't it? You can use feedback system, you can use feed forward system, you can use differential system, isn't it? Which one out of these available configuration is best for your system, that you have to select. And the last question, how the information taken from the measurement used to adjust the values of the manipulated variable. So what we are interested here is we are going to measure the control variable, isn't it? We also know which is the manipulated variable, isn't it? So if the control variable is changing from its set point value, how this information we can use in order to apply the external intervention. Whether the external intervention should be proportional to the error or some other law we have to use, that is what is asked in the last question. So this last question we have seen a little bit in more detail in the last class, isn't it? So we said that the simplest case is when the error is proportional to the external intervention, or how you can manipulate your manipulated variable, that should be proportional to the error, isn't it? So when we are using external intervention like this, then we are calling the control as proportional control, isn't it? So this is the typical example which we have seen, where we are saying that in this particular example you can see that FI/PI are the inlet, outlet is F&T. Your objective is to maintain the temperature inside the reactor. For a time being you are assuming that this FI is not changing, so this FI and this F is same, isn't it? So height of the liquid in the tank is not going to change. But if there is a change in TI, definitely the temperature of the reaction mixture inside the tank is going to change, isn't it? And your aim is to maintain this temperature to a set point. So what you are going to do, you are going to measure the temperature using temperature measurement. Then you are going to compare the measured temperature with the set point. And whatever error you are getting, based on that error, the temperature controller is going to modulate the steam flow rate to the reactor, steam flow rate to the stir tank heater, isn't it? So if you model this particular system, you can see that we get this equation: V rho Cp dt dash by dt is given as F rho Cp Ti dash minus T dash plus Q dash. All these variables, when I am representing by dash, these are nothing but the deviation variables. So how their values are deviating from their steady state values, that is what we are looking at. Okay. So this is the graph of the response which we are going to get based on whenever there is a change in the Ti. So you can see that at time t equals to 0, at time t equals to 0, you can see that the inlet temperature Ti, which was earlier at its steady state value Tis, changed to some new value, and because of change in Ti, your output variable T got changed, isn't it, from its steady state value. So what we have plotted here is T minus Cs. This is the output variable. So T minus Cs we have plotted. You can see that with this change in the input, how my output is going to change is represented here. Ideally, I am interested in having T minus Cs 0, even though there is a disturbance coming in the system, isn't it? So ideally, that is what I am interested in. But it's not going to happen in a real example, isn't it? In a real example, if there is a disturbance coming in, because of disturbance, your output variable is going to get disturbed. So the amount of change in the output variable from its steady state value, that is what is plotted here. Okay. So this is the equation. You can see that ultimately I wanted to, so see, if you look at this particular equation which is given in a deviation form, here Ts is the steady state value of the control variable T, Tis is the steady state value of the input variable Ti, and this Qs is the steady state value of the steam, the heat supplied to the heater, isn't it? Correct. Now if I look at this particular equation, in this particular equation you can see that the output variable is T, the input variable is Ti, and this Q is nothing but what? The amount of heat supplied by using the steam. So this Q is nothing but the manipulated variable which you can change. The question here asked is how I should change this Q in order to make this T minus Ts 0. Isn't it, all the time, even though there is a change in Ti present. Okay, so that is what the question we were trying to answer. So what we said is, we can have this Q minus Qs proportional to the error present. So error is T minus Cs, that is the error, isn't it? T minus Cs is the error. T minus Cs is the error. So depending on the error, I am going to apply the control action which is proportional to T minus Cs. So we have taken this Q minus Qs proportional to T minus Cs. That is what we have taken. Isn't it? So it is nothing but proportional control. So with this you can see that this proportionality constant we have taken as alpha, which is nothing but the controller gain, proportional gain we call it. You can see that as the value of alpha changes from 0 to higher value, you can see that you are getting lower value of the steady state error. So steady state error is the offset, isn't it? You can see that as alpha is 0, then there is no control. In that case, the steady state error is this entire difference here from 0 line. But as the alpha value increases, you can see that the steady state error is decreasing continuously. In order to have the steady state error 0, you need to have alpha value equal to infinite, isn't it? Correct. But you will not be able to use a very large value of alpha in a real life situation, primarily because this entire thing is based on the measurement, and the measurements are not accurate. Isn't it? In such cases, whatever the control action you are applying based on the error is actually based on the measured value, and the measured values are the values which occurred a while ago. It's not at the same time. What happened, beta? तबीयत खराब है क्यों उनकी? आप चले जाओ, प्लीज गो. जाना है आपको? So in this case, what will happen is, as the value of alpha increases, you are going to get the steady state error equal to 0, and in order to have the perfect control you need to have alpha value equal to infinity, which is not practical, because if you use very large value of alpha, there are the chances that you will get the invisible system, isn't it? You will have the instability. Okay. Alright. Now, clearly this particular control system is simple. Only one parameter is required. The drawback is you are not able to eliminate the error, isn't it? So then we said, can we do better than this? So what we said is, if we change the control action to an integral control action, in an integral control action what happens is, we will keep on increasing the control action as long as there is a error present. In fact, if the error is persisting for a longer period, you should be putting more and more control action. For instance, this case, you can see that the error is persisting for a longer period. It is not getting dying out. It's not dying out with time. So when the error is persisting for a longer time, then instead of taking the control action which is proportional to this error, instead of that, if I take a control action proportional to the area under this curve, basically your control action will keep on increasing unless the error becomes 0. Unless the error becomes 0. Isn't it? And that is the reason why when you are using the integral control action like this, you will see that your error is actually becomes 0 with time. But because of the problem in the measurements, you will have the oscillatory behavior. So when you are using the integral control action, your steady state error becomes 0, but then you will have oscillatory behavior. There is disadvantage with respect to the integral control action. Integral control action will eliminate the offset, but it will make your response oscillatory, isn't it? And if you increase the value of alpha, you will see that very soon your response is going to become unstable also. Okay. Alright. So then we said that can we eliminate these oscillations? Is there any way by which we can eliminate these oscillations? That there comes a derivative control action. So in the derivative control action, what we are doing is this additional term we have added. This additional term we have added. This additional term is doing what? This additional term is depending on how the slope of the error curve is increasing or decreasing. Based on that, the control action is modulated. Isn't it? So if you are taking a derivative of any function at a particular point, actually what you are getting? You are actually finding the slope of that curve. So in a way you are trying to find out how that function is increasing or decreasing. Isn't it? So it has the anticipatory property. Anticipatory property in the sense that you will be able to predict whether the function is increasing in future or decreasing in future. Isn't it? So clearly by using the derivative, you are adding the anticipatory behavior in the control action, and that makes your control system more stable. Why? Because you can eliminate the oscillations. You can see that whether the given control action is having the decreasing slope or increasing slope of the error curve. If it is the increasing slope, definitely you need to have more control action. If it is having a decreasing slope, then you have to restrict your control action a little bit so that the oscillations can die out. Isn't it? So you can see that with the derivative control action, even though there are oscillations present because of integral control action, all these oscillations get die out very soon if you are having the derivative control action. So this is nothing but PID control. Now the problem with PID controller is very good because it is eliminating the offset completely. It is stabilizing the process because of derivative control action. The only drawback of PID controller is you have 3 parameters to tune. Remember all these parameters, alpha dash, alpha double dash, these are the parameters associated with proportional controller, integral controller and derivative controller. All these parameters you will have to set. These are the user defined parameters. You will have to specify the values. And more number of parameters are there, more variables you have to tune. So that is the design. Okay. Alright. So this is what we have seen in the last class. Then we have seen this entire plan, that how the complexity arises when we are having the recycled thing. That is what we have seen in the last class. Okay. Let's move to the another topic, modeling consideration for a control purpose. Okay. So far what we have, remember in the starting classes, we have tried to appreciate why process control is required, isn't it, in the initial classes. Then we have said that, okay, for a process control we require a model, because unless and until you know your system, you will not be able to do anything, isn't it? After that we said, okay, let's look at slightly more detail about it. So we have seen the design consideration of the process control, which we have discussed recently, isn't it? Now we are adding some more detail. Some more detail we are trying to add here. Okay. So in this case, you can see that we are trying to make the model, and this model we are going to represent in a block diagram form. Why in a block diagram form? Because usually how the process control is performed. If you look at the earlier day, people used to make the hardware units, and each of these hardware units used to perform a specific task, isn't it? So if you represent your entire control system in terms of different blocks, and then you design the hardware units for each of these blocks, you can connect these blocks and control the process. That was the idea in earlier days. Now you can do this entire process control by using some programming language. Maybe you can use MATLAB. There is entire subroutine is there, Simulink or something, isn't it? Which you can use for process control language. Correct? But if you look at earlier days, before 90s, people used to make the hardware unit for each of these, modeling blocks which we get. Okay, so we are going to find out the blocks here, and then whether that is easy or difficult, that we are going to discuss, and how we can make our analysis a little bit more simpler than this. That is what we are going to discuss. Okay, so let's look at this usual system which we are coming again and again, isn't it? This is the same system we are looking at again and again. There is a start and hitter where Fi and Ti are the inlet variables, isn't it? F and T are the outlet variables. The steam is flowing through the jacket which is supplying the heat Q to the reaction mixture inside the heater, isn't it? My aim is to maintain the height, and my aim is to maintain the temperature inside the certain heater. Now for a simplicity, let us assume that this Fi and this F are same. So inlet flow rate is same as the outlet flow rate. For this particular system, if I look at the model equations, what are the model equations? dV by dt is given as Fi minus F, isn't it? If I am saying that the inlet flow rate is exactly same as the outlet flow rate, that means volume is not going to change. Volume is not going to change, and that means what? This height is not going to change. Okay, so the first equation is gone. We don't have to look at the first equation. What is the second equation? Second equation is d dt by dt is given as inlet flow rate Fi into Ti minus T plus Q by OCT. Isn't it? Where the Q is the amount of heat supplied by the steam. So this is the equation with respect to how the temperature is changing with respect to time, that we can get by solving this equation. There is no reaction occurring, so we will not get VdCA by dt. There is a third equation, how the concentration of A is changing, that is not required here because the reaction is not occurring, isn't it? Also, there is no reaction occurring, and because of that, one more term is there based on the heat of reaction that we have omitted, isn't it? Clear to everyone? So this is the equation, this is the appropriate equation for this particular system. Here, again for a simplicity, let us assume that the steam supplied here is a saturated steam. Steam which is passing through the coil is a saturated steam. So saturated steam, the amount of heat added inside the system will be given by what? Latent heat multiplied by mass flow rate, isn't it? So you can get the amount of heat added by this equation. Q is given as lambda into FST, where lambda is latent heat. Okay, so I can put this Q equals to lambda into FST in this particular equation, isn't it? So with that, this is the equation we have obtained. I can rearrange this equation little bit, so I can represent this equation as dt by dt. This becomes, so there are two terms Fi Ti, isn't it? And then Fi into T. So all the input variables I am representing on the right hand side, and all the output variables I am representing on the left hand side. So I can write down this equation as, after simplifying, we can write down this equation as dt by dt alpha t is given as 1 by tau into Ti plus k FST. Here you can see that this tau is nothing but what? Residence time. So Fi by V will be nothing but 1 by tau. Okay, and also this term lambda by V rho Cp, this is represented as K. Okay. Now, if you look at this equation, this is a linear differential equation. This is a linear differential equation, first order linear differential equation of initial value kind, isn't it? So, if the initial value, if you provide, you can solve this equation. In fact, we can get the analytical solution of this equation without any problem. Okay. So this is the equation we have obtained. You can see that left hand side has only the output variable. Output variable is the actual temperature T. Right hand side is Ti as FST, where Ti is the disturbance variable and FST is the manipulated variable. Both are the input variables, isn't it? So both the input variables I have taken on the right hand side, and the output variable I have taken on the left hand side. Okay. Now this equation is describing the dynamic situation. But let's say, remember at time t equals to 0, my system is at steady state. I am assuming that initially my system is at steady state, and at time t equals to 0, the input variable is messed up, and because of that I wanted to see how the control variables inside my tank, which in this case is temperature, is going to change with respect to time, isn't it? So initially the system is at steady state, so I can write down this equation as, this becomes 0, this becomes alpha Ts, and it is given as 1 by tau Tis plus k FSTs. So you can see that all the variables with subscript S are nothing but the steady state values. Let's subtract this equation from the original equation. If we subtract from the original equation, what we get is dt minus Cs dt plus alpha into T minus Ts, and that is equal to 1 by tau Ti minus Tis plus k FST minus FSTs. Okay. And I can represent this entire equation in a deviation form as dt dash by dt plus alpha T dash equals to 1 by tau Ti dash k FST dash. Okay. You can see that all these variables T dash, Ti dash, TST dash, all these variables are the deviation variables, deviation from their steady state value. Isn't it? See, this T dash is nothing but what? T minus Ts. So it is the deviation of the variable T from its steady state value. Correct? Here I have shown all these variables with dash, but later on you will see that I am going to omit this dash. So whenever I write down the model equation, it will be implied that the model equation is actually in the deviation. You will see that in this entire course, all the model equation we usually write in a deviation form. There is an advantage. There is an advantage in writing in a deviation form, and we will come back to that later. Okay. So this is the equation, this is the model equation which we have written in a deviation form. I can now get the solution of this. This is a linear differential equation. Solution of linear differential equation like this you can get easily. Isn't it? If you are having a linear differential equation like dy by dx plus py equals to q, its solution is given by this. Y into e raised to the power integral p dx, and that is equals to integral q into e raised to the power integral p dx to dx plus c. I can get the analytical solution of this equation by using this solution directly. This comes out to be T dash T comes out to be C1 e raised to the power minus alpha t plus e raised to the power minus alpha t in the integral sin 0 to t e raised to the power alpha t 1 by tau ti dash plus kfst dash. Again outside there is a dt. Okay. So this is the equation which we have obtained. I can put the initial condition. What is the initial condition? Remember this T dash is output variable. How much this output variable is changing from its steady state value. That is what T dash is. Isn't it? So where I am looking at T dash at time t equals to 0, what is this T dash is going to be? It is going to be 0. At steady state it is going to be 0. Remember we said that the system initially was at steady state. So at time t equals to 0 this T dash is 0. So if you put that, you will see that the C1 is actually 0. So you get this T dash equals to this last term only. That is what you are going to get. Okay. So when you are putting the initial condition when t equals to 0, T dash is 0, C1 is 0. So ultimately what you get is T dash t comes out to be e raised to power minus alpha t integral 0 to t e raised to the power alpha t and in the bracket 1 by tau ti dash plus kfst dash into dt. Okay, remember in the starting itself I said we have to represent this entire model in terms of block, isn't it? So in this case you can see that this Ti is the input variable, input disturbance variable, correct? This fst dash is nothing but what? It is the manipulated variable, that means it is also an input variable. So both these variables you know. So you can take this disturbance variable and this fst dash which is nothing but the manipulated variable. Both these signals are multiplied to, this Ti dash signal is multiplied to 1 by tau. This fst dash signal is multiplied to k. You can add these signals here, both signs are plus. So both these signals are added and this entire signal is there integrated here between 0 to t and multiplying these two factors, isn't it? So what people used to do earlier, they used to make a hardware unit for this part, hardware unit for this part and one more hardware unit for this part. Now whatever the input signals are there, you give these input signals to this hardware unit, that will convert to 1 by tau into this and k into this, isn't it? You add those signals here and that entire signal is given as an input to the third block. And this third block is going to solve this integral and finally it is going to give you the output. So that's how people used to do earlier. Okay, so this block diagram, there is a reason why we are representing in terms of a block diagram, because it gives you a easier representation of input and output. Now you can clearly visualize what is input and output. Here these are the two inputs, this is the output, and in between these blocks are going to modify your input information so that you can predict the output. Clear? Isn't it? But this particular model equation, this particular block diagram is still complex, still complicated. Isn't it? It's not easy. This integral you have to perform. It's not easy. We can simplify this particular model, block diagram further by using Laplace transform. We will see that as we go ahead. We will see that by using Laplace transform, this particular block diagram can be simplified further. Okay. But let's hold that question for a time being. We will come back to this again. Isn't it? When we will look at the Laplace. One more important aspect in modeling consideration is degree of freedom. Why degree of freedom is because if you are not matching your degree of freedom, usually you will get the erroneous result. Remember, if you are having n variables and n equations, you get a unique solution. Isn't it? You get a unique solution. Now enumerating how many number of variables are there and how many number of equations are there is easy if you are looking at a system similar to this. But if you are looking at a process control for an entire plant where you have 1000 number of variables and 1000 number of equations, finding whether the degree of freedom is exactly satisfying or not is not an easy task. Forget about this system. If you look at even the distillation column itself, in the distillation column itself, you have a lot of complications. Why? Because let's say if your distillation column is having 25 trays, each tray actually acts as a one system. And for each tray, you will have to write down 3 equations: mass balance, energy balance, and the component balance. So how many equations you are likely to get? For one distillation column itself, you will be having the equations more than 100. Matching the degree of freedom is very, very important. Why? Because in addition to this model equation, there are some more equations which are binding. For instance, equation of state, equations coming from thermodynamics, all these equations has to be considered in the modeling. Otherwise, you end up with getting the erroneous result. Okay. So the concept of degree of freedom is very, very important. We are going to look at that concept a little bit in more detail here. And there is one more important aspect of this, isn't it? Whatever the degree of freedom you are getting, that many number of control loops you require to be made, required to have in the system in order to specify the system completely. Okay, let's look at this example. So this is the same example which we are coming back again and again, primarily because then we can appreciate how these concepts are used. Okay, we could have taken a different example also, isn't it? In fact, in your book, the example of distillation column is taken. If you look at the book. Okay. So in this case, again Fi and Ti are the input, outlet are the F and T. Here the control variables are height and the temperature, isn't it? Again, in this case, the manipulated variable is Q. I can take the manipulated variable either Q or FFC. Both are same, isn't it? One of them. Correct. The equations in this case are, the first equation is A dH by dt, which is given as Fi minus S. So how the height inside the tank is going to change when there is a change in inlet feed rate, isn't it? Similarly, the another equation is AH dt by dt is given as Fi Pi minus C plus Q by rho Cp, isn't it? Now let's enumerate how many variables are there and how many equations are there. Okay. So in this case, how many equations are there? There are 2 equations are there. So number of equations are 2. And number of variables are 6. So these variables are H, T, Fi, F, Ti and Q. These are the variables. So 6 variables, 2 equations. So what is the degree of freedom? Degree of freedom in this case is 4. Isn't it? So number of variables minus number of equations, that gives you a degree of freedom. Degree of freedom is 4. Correct. Isn't it? If I wanted to specify this system, so what it means? Let's say in this case, if I wanted to solve this particular system, how many solutions are going to get? I am going to get infinite number of solutions. Number of equations are less than number of variables, isn't it? In this case there are 6 variables and 2 equations, so that means 4 variables you can fix arbitrarily. If you fix 4 variables arbitrarily, the other 2 variables you can get uniquely, isn't it? And I am saying 4 variables can be fixed arbitrarily means you can have infinite choices in fixing the 4 variables. So therefore the number of solutions in this case are infinite. Correct? Now I wanted to specify this particular system completely. That means I can specify the entire system completely only if the degree of freedom is 0. Only in case of degree of freedom is 0. So that I can do it easily. Why? Because whatever Fi and Pi are coming in, These Fi and Pi are actually coming from what? Remember, this starter heater is one equipment in the entire plant, and there could be some other equipment before this. Maybe there is a reactor from which the effluent is coming, isn't it? And if I am solving the entire plant, I am going to do the modeling of the equipment which is present before this, isn't it? And the modeling of that particular equipment is going to give me the values of Fi and Ti. So you can see that the inlet variables Fi and Ti, these are the disturbance variables. These are disturbance variables, but these are fixed by external environment. When I am saying these are fixed by external environment, means what? If I am designing the entire plant, I am also going to have the modeling equations for the equipment which is present before this, and that will be giving me the output variables Fi and Ti. This can be started. So in this case, Fi and Ti are coming. You can have here some measuring things you can have, isn't it? You can measure this, isn't it? So you can get the values of this, isn't it? You will not be adding this without measuring, isn't it? So even that measurement becomes one equipment, isn't it? So that is why this particular statement I am making here, this Fi and Ti are the disturbance variables. Their values can change. Their values can change, that means they are disturbance variables. But I can find out their value. And when I am saying I can find out their value, means they are fixed by external environment. Okay. So when I am saying that these inlet variables Fi and Ti are fixed by the external environment, I should not be considering them in calculation of degree of freedom. So what it means is, instead of having the degree of freedom which is 4 in this case, actual degree of freedom is 2. Actual degree of freedom is 2. Okay. So what it means is, if you can add 2 control loops here, you can specify your system completely. Adding one control loop is nothing but adding one equation. For instance, in this case, this H is the control variable and T is the control variable. If I measure this H and then maintain the H value by manipulating the outlet flow rate, I am actually adding one equation in this. Similarly, I can measure the temperature here and manipulate the heat supplied here. That is the another equation. So you can see that I can pinpointedly find out how many control loops required in the system. In this particular system, there are 2 control loops required, one for temperature and one for height. Remember, I said that you can get some additional information. You can get the additional information from degree of freedom, and that additional information is you can find out how many control loops are required additionally. I इतना जोर से बोलने के बाद भी लोग सो रहे हैं. थोड़ा कम पिक्चर देखा करो रात में. ठीक है? So see, I have also been the student earlier. I know what you can do, isn't it? मैं तो कहीं आसमान से तो टीचर बन के नहीं आया ना. I have also been there on that side earlier. So I can pinpointedly, predict. रात में पिक्चर कम देखा थोड़ा. ठीक है? तो आप क्लास में थोड़ा अटेंटिव दिखोगे. And unless you reciprocate, there is no fun for me. Otherwise, I am only burning my energy. You are not at all interested, isn't it? Attendance is compulsory and that is why you are coming. But you are only physically present. Mentally you are not here. So what is the point? Okay. So see, you all cry later. People are not taking academics seriously. But try to see yourself in the mirror also. You will find it is not one way. It is 2 ways. Correct? Unless you reciprocate, I will not have that, I will not get that inspiration. तो हर साल मुझे यही पढ़ाना है. अब तो मैंने सब कुछ बना दिया, स्लाइड वाइड सब बना दिया. पहले तो एक्चुअली ब्लैक बोर्ड पे पढ़ाते थे. ठीक है? So please don't do that. Please help me. I am requesting, please help me. Okay? So give me some inspiration so that I can, do some more hard work, so that classes becomes more lively, You will also enjoy. This subject is really interesting because this particular subject has concept from all the subjects which you have done so far. You will find mathematics, you will find optimization, you will find reaction engineering, heat transfer, everything is there. Okay. And not just that, whatever the concept you are going to learn here, you are going to use that later also. Not necessarily in chemical engineering. Some other applications also you will be able to use. So this particular subject is slightly odd man out in engineering. Okay. You should be interested in this. So okay, I am sorry to say this, but please make the classes lively. You ask me as many questions and I am happy. If you are not asking the question, I can figure out by looking at your eyes whether you are interested or not interested. Now I have been in this system almost how many? 12, 13 years. I can figure out this. Okay. So degree of freedom is very, very important, primarily because it is going to give you a information that how many control loops are required. Isn't it? So when you are trying to model a particular system, if you can find out degree of freedom exactly, you can figure out a priori how many control loops are required. Okay. And that information required to be found out when you are designing a plant, big plant. I am not sure how many of you will join the chemical process companies, I don't know. Maybe you are interested only in finance, isn't it? But there are also these concepts you are going to use. Believe me. Okay. Alright. Let's look at another interesting aspect. So see, this is a first level process control course. This is the first level process control. In this first level process control course, we are only interested in linear process control. Only in the linear process control. We are not interested in non-linear process control. Okay. But usually we get a non-linear equations, non-linear modeling equations. So in such cases what we do? We linearize this non-linear equation. Why we are looking at the linear equations? The answer for that is, maybe I can give the answer here itself. Remember I said that all these model equations we are going to solve by using Laplace transform. Okay. Why Laplace transform? Can anybody tell me? Why Laplace transform? These are very commonly asked questions in the interview. Why Laplace transform is used in process control? What is the name? That I have said, but in what way it is used? In what way it is used? Tell me. By using Laplace transform, how these equations are going to get simplified? Tell me.
It linearizes multi-degree differential equations to first order.
And what will happen to first order equations? We are having one first order equations.
They are easy to solve using Laplace transform.
So, I understand. That is what I am saying. It is easy to solve by using Laplace transform. But how? I am asking how.
We already have solutions for that.
That's not that. That's not that. Okay. So if you are having a differential equation, if you take a Laplace transform of differential equation, what you get? You get algebraic equation. Okay. And solving, remember in this case you have simultaneous differential equations is what you get if you model a particular system. A typical example is CSTR. You get three equations: how the concentration is varying with respect to time, how temperature is varying with respect to time, and how height is varying with respect to time. And all these three equations you have to solve simultaneously. Now solving multiple simultaneous differential equation is difficult compared to solving simultaneous algebraic equations. If you are having algebraic equation, you can apply the Gauss-Jordan elimination and you can get the value. Isn't it? Linear equations you can solve. And that is the reason why we are using the Laplace transform, because Laplace transform is going to convert your differential equations to algebraic equations, and dealing with algebraic equations will be easy. Okay. Then we come to the next question. Why linearization? Because if you linearize your differential equation, The linear differential equation is going to give you a linear algebraic equation. Linear equation you are going to get. But if you are having a non-linear differential equation, you will get a non-linear equation. Non-linear polynomial you are going to get, isn't it? So there, again the solution will require numerical method. But if you are having the linear equation, it is easy, isn't it? So that is the reason why we are focusing only on linear process control. Non-linear process control can be done, but that is the part of advanced process control we are not going to touch there. Okay, maybe towards the end, probably I will give you some information on that, but not now. Okay, is it clear? So now let's look at the linearization. So linearization typically we do by using Taylor series. So in this case, let's say this is the differential equation given dx by dt is given as f of x, where function f of x is a non-linear function. Function f of x is a non-linear function. I am going to linearize this non-linear function f of x by using Taylor series expansion, isn't it? So this f of x I can represent using a Taylor series expansion like this. You can see that f of x is given as f of x naught plus df by dx. So this derivative I am finding out at x naught into x minus x naught divided by 1 factorial, and there are all higher order terms are there, isn't it? If I omit this higher order term and if I retain only this first order term here, that means what if I am representing f of x as f of x naught plus df by dx as x naught into x minus x naught. This particular equation is nothing but the linearized equation. Graphically what it means, I am finding out the function value here by taking the tangent at this point, isn't it? Correct? So now you can see that in this particular case, why I am saying it is a linear equation, because this term, this derivative term is actually nothing but what? Constant. You are finding out this derivative and you are finding out this derivative at x naught. So you are going to get a constant value here. Isn't it? Only variable in this particular equation is x. X naught is also known to you. So only variable is x. So this equation you can see is a linear equation. Even though this f of x is a non-linear equation, but after expansion and only retaining the first order term, this particular right hand side is a linear term. Okay. Now this is when I am having the expansion of the function which is having only one variable. But let's say if you are having two variables, x1 and x2. In that case, the Taylor series expansion will be given by this. You can see that here also we have retained only the first order term. So you can see that I am having two differential equations, dx1 by dt, and that is equals to f of x1 x2. So function f1 is a non-linear function, and similarly dx2 by dt is given as f2, which is again function of x1 x2, and I can expand this f1 and f2 by using Taylor series expansion. So Taylor series expansion in this case for function f1 is given as f1 at x10 x20 plus dou f1 by dou x1. It is calculated as x10 x20 multiplied by x1 minus x10 plus dou f1 by dou x2. Again this derivative is calculated as x10 x20 and multiplied by x2 minus x20, and similarly we can expand f2. It looks very easy. But believe me, a similar examples I have given in the earlier exam. People are not able to solve. In fact, the same example I have solved here. This is the same example people were not able to do it. Okay. So don't be in the wrong impression that you will be able to do it easily. Unless you practice, you are not going to do it. Okay. Alright, so we will stop here.
बात मान अरे राजन भाई क्या ही कर ये वही ये फोर कोर्स है ना।